knowledge about the history of X-ray crystallography, but because he knows practically everybody in X-ray crystallography. And that helped me greatly in getting the speakers. I must say, nobody turned us down, which was fantastic. I also wish to thank the British Crystallographic Society. It's not a joint meeting, but the British Crystallographic Society have been incredibly supportive. They publicised the meeting, I'm sure that's why many of you are here, and they paid half the cost of making this a hybrid meeting, which enabled people from overseas to be here, not in person, but virtually. And the talk will be recorded, and it will be put on the Historical Group YouTube channel, I hope within the next month. So if you want to look at it again, please do so. And I think it will be an absolutely fantastic historical record, because we have absolutely fantastic speakers today talking about people, in most cases, they know about very well. So without any further ado, I hand you over to the chair of the first session, Mike Glazer.
Okay, thank you, Peter. When Peter approached me some time ago about this idea, of course, I was very enthusiastic to be involved. I'm always trying to promote crystallography, even X-ray, electron, whatever. So I always value that opportunity. Crystallography probably doesn't need much introduction, or X-ray crystallography itself, to many people here, but just in case there are those who wonder what this is all about. So this is a subject which, as the name suggests, is all to do with crystals. And it has a very long history. And some of you may not realize that actually there is evidence that crystals were being studied or being admired or treasured probably about 1 million years ago by ancient hominids, because they used to collect, there's evidence they used to collect crystals in their pristine condition. And you have to ask the question, why would they do that? So I've always argued that maybe this is the reason for the development of the human mind, that it began with crystals. And there are reasons to think that. So today we have a collection of talks from different people. And as Peter said, there are many other crystallographers in this country who could equally well have been talked about. But of course, limiting of time means we had to be a bit selective. Britain has a formidable reputation in crystallography, starting really with the Braggs, W.H. and W.L. Bragg, father and son, in the early part of the 20th century. And it's because of them, really, that we are here today, because what they did carries all the way through. Now, many of us here who are crystallographers look back through their PhD supervisors and so on, trace back to either W.H. Bragg or W.L. Bragg as their scientific grandfathers or great-grandfathers. In my case, my PhD supervisor was Kathleen Lonsdale, who you're about to hear about, and she was a student of W.H. Bragg, so I consider W.H. Bragg as my scientific grandfather. And there are others here similarly. And again, you're going to hear about Bernal, who again was a student of Bragg. So there is this connection all the way back. Okay, so I think that's enough for me to say at the moment. So I think I'll get on with the first talk. And the first talk is John Finney, who's talking about Desmond Bernal. John.
So, Bernal, being born in 1901 in Ireland, before independence, was actually a British citizen, although he continued to insist on his Irish background. This is where he was brought up. It's an estate in north of Limerick in Tipperary, and we actually visited there about 20 years ago. And it's a very sort of exciting site, and one can understand why the environment was stimulating to a young lad like Bernal. He lived his life to the full, and he liked to say that he thought his biography should be written in 4 colours. Signs to show the interaction between the different parts of his activities: science, politics, arts, and his personal life, and how they fitted together. Oral tradition differs as to the colour of those pages. He liked to say perhaps his science was black and white, his politics was certainly red, his arts you might think of as blue, and his personal life perhaps purple. But I'm afraid time restricts me to talk only about his science. So really he did a tremendous amount of work in the early days of crystallography, and I'll just try to go through some of the pointers which I think have led to the development of things later. So a short potted early scientific history. He did his undergraduate work in Cambridge. He didn't just bother with the natural sciences tripos, which some of us have been through and was pretty tough. He actually did the mathematical tripos at the same time. And in addition, he studied physics, chemistry, geology, and mineralogy. But those didn't seem to be enough to challenge him. He became fascinated by the possible arrangements of atoms in space. And so in his third year, in the vacation, he worked out mathematically 230 space groups. This was too long to publish, even in the cut-down version, but he was awarded a prize for it. In fact, it's been republished since, and if you look at this, not only is it an amazing piece of work, but considering it was typed on a manual typewriter by his poor soon-to-be wife, Eileen Bernal, is actually itself a tour de force. Anybody's welcome to look at that, but please don't take it away. After his undergraduate work, he needed to go somewhere, and the thought was he might actually go to the Royal Institution. And this is what the recommendation from Hutchinson in Cambridge said to Sir William Bragg. And it's rather nice. I mean, thick, typewritten manuscript, rather the air of a dog bringing a poached rabbit to his feet. I was quite amazed, a remarkable effort for an undergraduate in his third year. And Bernal liked to tell later of Bragg's response when he reminded him of his thesis on space group. The great man didn't read it, he probably wouldn't be able to understand it. But the first page was sufficient to show that this young man was worth encouraging, and Bragg took him on at the Royal Institution, where he did a certain amount of very early work in crystallography. He determined the structure of graphite. Now, that may seem fairly trivial. At the time, it wasn't. But the fact that he determined the structure, managed to explain or sort out an argument at the time of why diamond and graphite, both being carbon, had very different physical properties. So establishing, if you like, the relationship between structure and property. He worked on the crystal structures of bronzes, and typically he gave away this problem, as well as many others, to others. And this is really quite typical of him. He would come up with an idea and a line of work and pass it on to another group, another person, and not expect to get any credit for what actually was done. At the RI, he developed instrumentation, and the first rotation X-ray camera was actually produced, and this is a picture of it. And it consists of an alarm clock, a piece of brass tubing, and a couple of bicycle clips to keep the film in place. And using this and rather better developments from it, he began to take rotation photographs like this. But then how do you interpret these? Well, I mean, let's make it easy. Let's produce something that some of us will remember using in the early days when we were trying to solve crystal structures using a rotation camera, the renowned Bernal chart. So not only was he solving structures, he was developing techniques for other crystallographers to actually use. In 27, after 3-4 years at the RI, he moved to Cambridge as the first lecturer in structural crystallography. Many new structural investigations, as you can imagine, in the early days of the field, there was a lot of things to be done. The field was wide open. To help him, he developed a flat plate X-ray camera, one developed on from the rotation, And particularly fruitful was his work on sterols and sex hormones and proteins. And many of us know the story of the first photograph he took of the crystal pectin in the atmosphere, a dried sample. There was no sign of any spots. So he and Dorothy Hodgkin, who was working with at the time, she was his PhD student at the time, were rather disappointed. But Bernal went back in the lab and he actually rehydrated the crystal and took a picture of it and found there were lots and lots of spots, and spent apparently the night wandering around Cambridge thinking about now what he could do, having discovered that proteins would diffract in such a way that perhaps one can get back to their structure. There's a picture of Dorothy with Bernal. No doubt we'll see more pictures of Dorothy as we move on. He also began work on viruses, or integrated work on viruses with Irsdorf and Kuchen, and his first work on the structure of water was published in 1933 while he was still in Cambridge. And I'll talk a bit more about that later on. I'll actually hear a bit about, on the line of what Mike was saying in terms of who fathers whom and who your grandfathers are. In 1938, Bragg, W.L. Bragg, moved to Cambridge as a Cavendish professor and essentially took over Bernal's lab, because Bernal was refused a job in Cambridge because he was actually not particularly a favourite of Rutherford, who was the previous Cavendish professor. And he was really at odds with the Cambridge establishment, as many as have been also. So his lab in Cambridge was essentially divided up. Some was kept by Bragg, and some Bernal took with him to Birkbeck. And if you look at what happened in Cambridge after Bernal left, he appointed Perutz before he left to work on hemoglobin. He was later joined by John Kendrew to work on myoglobin. And Bragg continued the tradition of encouraging biological work in Cambridge, and also from the same lab came the double helix DNA structure. And in 1953, Bragg moved to the RI, and there David Phillips determined the first enzyme structure. So you can see this trace through of what Bernal started moving down through the scientific world. In 1937, as I say, he was refused tenure in Cambridge and moved to Birkbeck. And after the war, we'll see a little bit about the war in a few minutes, there was work on proteins, which was done with Aaron Klug. Early computers, he realized that as crystals got more and more complex, then one might need computers to try to understand and solve their structures. Viruses, which he employed Rosalind Franklin, and Aaron Klug at that point joined Rosalind in that work on viruses. Liquids, which uncharacteristically he kept to work on himself. Cements, trying to understand the structure of materials and their function. This is post-war, rebuilding, etc. And also ideas of generalized crystallography, which Alan Mackay has taken on since. And when one opens a new laboratory, it's usually bright and shiny, nice and modern. Bernal's Biomolecular Research Laboratory was 2 war-damaged houses in Torrington Square. But even so, Lawrence Bragg was happy to come and open it. And a little diversion into the arts, Bernal's had a flat on the top floor of number 21. And one evening, there was a party for which a certain Pablo Picasso was present. And after a few drinks were taken, perhaps, Picasso decided to write something, not on a piece of paper. The piece of paper wasn't big enough, so it was put on the wall. And this has passed down since, together with the wall on which it was built, to various places, and currently, I think, resides in the Wellcome Trust. There's a story about that, which we can read later. Nobel Prizes, Bernal never got one. Many of his students did. Aaron Klug, Dorothy Hodgkin, Max Perutz, John Kendrew. During the war, he was appointed scientific advisor to Mountbatten, who was the chief of combined operations. And he was a great believer in science as, well, he saw science as being necessary to try to get over the problems of the war. And a number of achievements, which I won't go through, but he made a statistical analysis of the effects of enemy bombing and of explosions, which the military didn't like because it went against what their conventional wisdom was. There's this lovely project of floating ice aircraft carriers, so-called Project Habakkuk, which was worked on not only by this guy called Geoffrey Pike, who worked out that if you mix ice with straw, then you get something which is as strong as concrete. But Max Perutz was also involved in that work. And finally, the Normandy landing required an understanding of the nature of the beaches in order to try to get a reasonable landing. And he worked out the best places to move, or best places to choose, from his holiday members on the Normandy beaches. But also, a call went out to people generally to say, please send in your holiday snaps. And they did, and he worked through his snaps, and the result of that was a decision on where to do the landings. And we all know about what happened there. I don't think we need to talk too much about the problems of war at the moment. But in terms of the Normandy landings, here's a little comment. In going over one of his 2 visits to the beaches beforehand, he committed the frightful solecism of not knowing which was port and which was starboard. Right, I'm going to say a bit about non-crystallographic science. You define crystallography as systems built on lattices. It's liquids. What's the structure of this stuff? Why? Why would you want to know? He said the interest came through his interest in biochemistry, and all living structures are mostly composed of water. So therefore, if one understands the structure of water, it might help us to understand the way living things function. And this was to lead to a seminal paper in 1933, published in the first volume of the Journal of Chemical Physics. Now, 1933 was very early on in the years of crystallography, only 20 years since X-rays were first diffracted from a crystal, and barely a decade since the first methods of working back from a diffraction pattern to a crystal structure was successful. The Bragg equation, the Lau equation. So how do you interpret the structure of a pattern like that? It doesn't show on a white background. The top pattern. The bottom pattern you'll recognize as simple crystal powder pattern. The top is a diffraction pattern from liquid water. And no way you're going to interpret that. How are you going to try it? Well, a Dutchman called Prince suggested that you could associate these weak peaks, these broad peaks, with atomic spacings through Bragg's law. And working on that basis, having some idea of what the structure of water was like from the spectroscopists at the time, Bernal worked out the suggestion that in fact the water molecules should interact with each other in this sort of tetrahedral form. And if that's the case, then something will come to mind. Same sort of thing as you find in silica. Various structures of silica, they're fourfold coordinated, tetrahedral coordination. You're building together tetrahedra into a regular crystalline structure. And he picked on 2 different structures, one of quartz and one of tridymite, and tried to fix the X-ray data to a mixture of those structures. So he proposed that liquid water is some kind of disordered version of a quartz-like structure, mixed with some tridymite-like structure at low temperature, which would explain why water has a temperature of maximum density, and also would explain why ice is denser than the liquid water, actually less dense than water. And this would approach an ideal liquid at high temperature. And he used Prince's approach to try to justify this. And this is a slide taken from a copy of a original paper, actually, I have up in my loft somewhere. And you can see that the experiments and the model for the time is actually pretty good sort of agreement. It's not something we'd accept today, but think about when this was in 1933. It's a pretty impressive sort of result. So the summary of this paper, it set out the essence of the electronic structure, the local geometry of the interactions. He saw the liquid structure as a disordered version of a quartz-like structure, and it explained many of the important properties. And there's a list of some of them there. So it looks pretty successful. But he criticized it himself some time later. He saw this was one relief crystal structure, trying to picture water as a structure, as a mixture of different crystals. And this didn't really seem quite right to him, because water flows, crystals tend not to. And so he said this was going to prove a delusive approach. It postulated a greater degree of order in the liquid than actually exists there. And so he went back to the problem. Initially through looking at the structure of simple liquids, like liquid argon, for example, liquid inert gases. And he tried to get a picture of an approach to the liquid that fulfill these criteria. You can actually see a picture of the structure. It is simple, Occam's razor, homologous to a crystalline structure, as well as really different in kind, and a general quantity of homogeneity. And this is the message he came up with. The liquid is a homogeneous, coherent, and essentially irregular assemblage of molecules containing no crystalline regions. What does that mean? Well, simple. That's a crystal. The key concept: crystals are regular piles of molecules, liquids irregular heaps. A very, very simple concept, but one which had eluded theoreticians for decades. And in fact, he apologized to the theoreticians. The modern theoretical physicist, I apologize for introducing such a simple way of looking at things, but I believe on the whole, it's better to start with a model that there's some resemblance to reality. It's quite a criticism of the way science, or theoretical science, was done on liquids at the time, which were largely based upon distorted crystals or dense gases. And neither approach was capable of explaining the structure of liquids. There was one theoretician, at least, who disagreed with this, John Finney, who was a major operator in condensed matter physics, and is on record as saying this is now seen as the key to any qualitative or quantitative understanding of the physics of liquids. Not classical crystallography. Bernal wasn't bound by classical crystallography. He thought classical crystallography was one point in this whole array of considerations of structure. So how do we apply this to water? Well, very simply. There's the local tetrahedral coordination. You can build that structure into a crystal, ice, or lots of different structures of ice. And now about 15, 16, 17 different structures of ice, depending on the temperature and pressure. And they all have this as their building motif. But I want to, how can you actually build this into a model of water which is non-crystalline? Well, you try to construct a model of tetrahedrally coordinated molecules which are not crystalline. And that he did. Simple model. And I think if you look at that, you'll see there is no sign of crystallinity at all. And you can build another version which is perhaps a bit more illustrative. The structure of hexagonal ice, drawn with these so-called spaghetti models, and liquid water, this way in which you can join together these water molecules, four coordinated, which are in a non-crystalline fashion. Or if you want a two-dimensional analog, simply something like that. That's a picture again from up in my loft of his early attempts on fitting this model to the diffraction data that was available at the time. This was the model. This is the radial distribution function of the model that he produced. And then it gets polished up and gets published as a comparison of experiment and theory. And again, for the time, it's a pretty good model. I've seen worse agreements than this between some computer simulations done much, much later and the actual structure of the liquid itself. So his final view of water, essentially a random network of water molecules. Each water molecule essentially interacts with its neighbors in an approximate tetrahedral manner. The local coordination is ideally fourfold, but there is some variation, as one would expect in a disordered system. How good is it? It explains the main properties. It explains expansional freezing, explains temperature, maximum density, can be used to explain the mobility of hydrogen, structural changes with temperature and pressure, and perhaps most importantly, it's consistent with the current state of art experimental work. There's a picture there of our current view of what Whittaker water looks like. We know much better experimental data from neutron scattering and much better ways of interpreting the data, and the concept is seen to be essentially correct. There's a major change in an understanding of liquids in general and of water in particular. And it's begun to help us to understand some aspects of water's biological role, which was where he came in the 30s. How is water relevant to biological systems? Here's just two structures here, one of the water in papain, showing you some of the interactions which help to keep the protein stuck together, and some other work from on the vitamin B12 coenzyme, which was lubricated very helpfully by Dorothy Hodgkin when we did this work, trying to understand the structure of water in these systems and how they might relate to the stability and, in fact, the binding of, for example, of substrates to proteins. So, a bright young chappie, this is where he came from. The Irish have finally grasped the significance of Bernal, and in fact, in Limerick, there is this plaque celebrating his birth and his science, and it is, in fact, has led to the growth of the Bernal Institute in the University of Limerick. I've done no more than rush through stuff. There's an awful lot which you will read if you can get hold of a copy of Andrew Bound's biography of Bernal, which is a real tour de force. It goes through all the bits of his science, his arts, and his other aspects of his life. But if you can't get hold of a copy and you don't want to read 500 pages, then there are some interesting bits and pieces in a recent history of crystallography news, which some of you will have got. There's a copy here if anybody wants to actually have a browse through it. So I think I'll stop there. Thank you very much.
No. We need to get them over.
Oh, wait a minute.
Oh, I could have talked for longer.
Interesting that the first three talks we got are all Irish.
So what is in the Irish psyche then? Is it then the Irish psyche which pushes them towards crystallography?
How are we doing? All right. I was just saying to John that it's interesting. The first three talks this morning are all Irish. They all came from Ireland. Something odd about that. So, do we have any questions for John? Not on the internet.
Before we start, my name is also Irish.
As a fellow Irishman, can I pose this question? Did Bernal do any work on the structure of ice as well as on water?
Not specifically. He recognized the structure of ice in his 1933 paper on water. The structure of ice was solved by Barnes published in 1926, but Mike was telling me earlier on that Helen McGaw solved it earlier. But no, I don't believe he did any work on ice. He probably didn't think he needed to. Incidentally, Bragg also predicted the structure of ice much earlier from theoretical considerations and a bit of knowledge of the properties of ice.
So in front.
Sorry, I'm puzzled by this movement of hydrogen. You surely don't mean hydrogen gas. Hydrogen ions?
Sorry? So you're talking about the movement of hydrogen
The movement of hydrogen, yes.
in water and in ice.
Is this H2 or H plus?
There's arguments about there are still arguments about the nature of the conductivity of ice and of water. There is essentially the proton moves around, can move around. Water itself isn't purely H2O. It's mostly H2O, but mixtures of H3O plus and OH minus. And you can work out a way of moving the proton through both the lattice and through the liquid through that way. But when you start thinking about the quantum nature of the processes, then things get a bit more complicated.
You suggested that Bernal's time at Cambridge was compromised by his relationship with Rutherford, or the other way around. But did his politics have anything to do with it? And just as a continuation to that, how was it that he was considered safe during the Second World War to be a scientific advisor if his politics were as red as they might be?
With respect to the first question, I cannot give a definitive answer, but I suspect there could have been some political issues involved, but I don't know. It's recorded that that Rutherford wasn't a fan of his, and the reason he wasn't a fan of his, I cannot say, but one suspects it might have been political.
One explanation, I think, could be that he was a communist and very well known in Russia. Russia were the Allies at the time.
Yeah.
So maybe that was the reason.
Yeah, I mean, I have another slide there which talks about when he joined the Communist Party. I think it was 1927. Now, the second part of your question, he was recognized as having the kind of mind which was very fertile. And the cabinet member who forced him through, there's a quote in the slides there, that I don't care if he's as red as the fires in hell, I want him on board. And looking at the sort of things he did is really quite impressive. They're not crystallographic, but they are the workings of a fertile scientific mind, looking at the evidence, insisting on the evidence before you come to a conclusion. And as I say, the book tells you a lot more about it. There's a whole load of stuff there about the war work, and there's a bit in the crystallography news issue as well.
I seem to remember a really neat experiment that he did for liquids, which he took ping pong balls, put them in a big container, poured in paint, and after it dried, it took all the balls out. You could see the bits of the balls that weren't painted. You get all the contacts between the different molecules. And then from this, you could then construct these diagrams that John showed you.
Yeah, I mean, one of the pictures I showed, that picture I showed of a heap, was one of those paint stuck together models.
And it shows how inventive he was.
Yeah, but you know, when I turned up at Birkbeck in '66, my job was to produce a more accurate model. And we'd progressed then from using steel balls and paint to steel balls and wax. And that model is still being used today by many people, not just in terms of understanding liquids, but in understanding things we shouldn't be doing, like oil extraction, etc., etc. Yes. Irregular packings are used in all sorts of chemical processes, and the structure that was Bernal actually developed there is relevant to those two.
Take one more question.
Thank you, John. Could you comment on, in my lab, we have water at 18 megaohms, which is rather resistant, I think, and the hydrogen transfer in water, you were mentioning that before. So I guess if you've got pure water, it's rather resistant to conducting electricity, and if you put a little bit of salt in it, it does conduct.
It does conduct, but it's a very low conductivity. I'm not sure what you're asking. You're asking me to explain the details of the proton transfer process.
Right, so I think we'll move
Okay,
on.
thank you.
John.
Okay.